Hello, class. um, I wanted to finish up the supermesh analysis rather quickly so that we could get on to the next topic that we were going to do. So I'm not going to take a lot of time to do this, but I want you to understand, how to do supermesh, just like you understand how to do super nodal, right? So we're doing it very similar. You might want to go back and look at the supernode analysis to see what we're doing. But see, I've got 1 and I've got 2, right? It's going around, that would do this loop. That's going around, that would do this loop. So this is going to be I1 and I2. And so what we're going to do is we're going to take this out, as I've done down here. We've taken that out, and then we're going to do a supernode, or excuse me, a super mesh analysis over the entire thing. But we do know something, right? We know that at that 4 amp that I've taken out there, we've got I1 going that way, and we have I2 going that way, right? I1 and I2. Now, we know that I1, which is going in the same direction as the 4 amps, so we know I1 minus I2 is going to equal 4 amps. So let's keep that as our first equation. All right, that's our first equation. Now, what we want to do is we want to do a super mesh over here. And now watch what I'm doing. I've removed this and I've put an open circuit there. But let's look at my summation as I go all the way around here. We'll start right here with the 20 volt power supply. So I've got 20 volts. And again, like I do it, opposite to the way your book does it, but much more along the convention of the way that it usually is done. So 20 volts positive, that's the minus to the positive. Might need a new pen soon. And then I've got 6 ohms. Now I'm going to say that this is I, right? Actually, no, what am I talking about? I've already done that part. I'm going to say this is whatever the current is. So this is going to be I'll use capital letters, I1. So 20 volts up. It's getting late. I'm not even using the correct 20 volts, positive 20 volts, minus 6 ohms times I1. I'm going to get it down. Next one, minus 4 ohms. Now, is that still I1? Yes, that would be I1. Minus 2 ohms. But what's the current of our 2 things that is flowing through that 2 ohm one? Isn't that I2? That's right. So that's I2. And then I'm going from the minus to the positive, so that's going to be plus 12 volts, right? And all of that equals 0. So why don't we simplify that a little bit. So I've got 20 volts plus 12 volts. That gives me 32 volts. And then I've got, and that equals, and we'll take these minuses onto the other side. So I've got minus 6 and minus 4. That gives me positive 10 ohms, because I'm taking it to the other side, times I1, right? And then we've got the minus 2 ohms times I2, but I'm taking that to the other side too, so that's plus 2 ohms times I2. Now, we can easily substitute this in, because if we want I1 in terms of I2, I could say that it's I1 equals 4 amps plus I2, right? So let's just substitute that in. 32 volts equals 10 ohms times 4 amps plus I2 plus 2 ohms times I2. All right. Now, the first thing we can do is we know V equals IR. Let's always write that up there. V equals IR and P equals IV, right? Okay. So we see that 10 ohms times 4 amps, right? I times R is going to be 40 volts. So we'll just write that there. So 40 volts. And then 10 ohms times I2 plus 2 ohms times I2 is plus 12 ohms times I2. Well, let's subtract that off there. So I've got 32 minus 40. That gives me minus 8 volts, right? Is going to be 12 ohms times I2, or I could say that I2 is going to be minus 8 divided by 12 ohms. Okay, I'm hoping that's right. 8 divided by 12, it should be 0.6666, so minus 0.667 amps. And then I1, right? I1 is just 4 amps plus I2, so that would be 4 amps minus 0.667 amps, and that gives me 3.333 amps equals I1. So there you go. I1, 3.33, I2, 0.667 amps. For both of those two cases. And there you go. We've solved that problem. I'm just going to stop this and make sure I haven't made any mistakes. I want to look back at my notes here. Okay, class. I'm sorry I went away to draw this circuit. We are also working on superposition on this time, and so I want to describe superposition. We actually have like, 25, 27 minutes left or whatever. So we've got plenty of time to work through this problem and to introduce superposition. Superposition really says that I can take one of the power sources away, look at the circuit without that power source in there, and then replace it and take another one out. Like I could take out this voltage source and replace it with a short circuit, and then look at what the circuit will replace both of these with a short circuit, and then look at what the circuit would be like with this, and then I could put both of those two back. I could take this out and then and replace that with an open circuit. So here's how we do it. Let's look at the procedure of superposition. Superposition says that I can take one of the power supplies, whether it's a current source or a voltage source. I can take one of those out or two of those out, and if I replace a voltage source, so let's put superposition, but let's say replace a voltage source, right, with a short circuit. Short circuit. So we replace voltage sources with a short circuit. We replace current sources with an open circuit, right? So I replace those. So, and then I look at what the currents are due to the other voltage or current sources that are left in there. And then I add those two currents together. Right? So what I want to do with this is I really want to redraw this circuit. In fact, the first thing that I want to do is I want to take this circuit and I want to redraw it in a way that, you know, is schematically still correct. Let's put that in there. And but I want to draw it with both of these two things replaced. So I would go over here. Now, what I want to do is I want to look. These are in parallel with each other, right? So let's just draw that. Let's draw that in parallel so that we can use our inverse lever current divider law that I've taught you, right? How to find out how much are going between the two. And that's 6 kilo ohms, 12 kilo ohms, 14 kilo ohms, and 35 kilo ohms, right? Okay, so I'm just going to put 6K here and 12K here so everybody can see that. Now, what have I got in here, right? Right now, if I take that voltage source out and replace it, like I said, replace voltage sources with a short circuit. Replace these with an open circuit, right? So I'm replacing that, and then I'm going to draw the other ones here. I got 2 more resistors coming down in parallel, like that, right? And then that's my circuit. So this is going to be 35K, and this is going to be 14K. And so this is how I've now drawn the circuit, and this is still 6 milliamps as far as the, so I can do that, and then what I can find is I find out how this is traveling through here. Let's say that I'll call this with just the voltage source replaced, the current source still there, 6 milliamps. So if I've got 6 kilo ohms and 12 kilo ohms, how is the 6 milliamps that comes up here going to split between those two? I think everybody can see, well, I'm going to get a lot more going through the 6 kilo ohm resistor than I am the 12 kilo ohm resistor, because the 6 kilo ohm resistor has less resistance to current flow, doesn't it? So let's do that. So the first thing that we're going to analyze is with the current source. Right? We've taken the voltage source out and we've replaced the voltage source with a short circuit. All right? Now I've got 6 milliamps coming in here, and it's got to divide out between these two. We can use the inverse lever rule, right? So if I want to find out the current that is flowing through the 6K resistor, I would use the total current that's flowing in, 6 milliamps, times the ratio of the opposite. That's why I call it the inverse lever rule, right? I'm trying to find out the current flowing through the 6 kilo ohm resistor, so I use the 12 kilo ohm resistor over the total, 18. And that tells me how much is flowing through the 6K. So 12 kilo ohms divided by 18 kilo ohms, right? Does everyone see how that works? Okay, now we're going into this part down here. And, well, anyway, we can figure this out. So we know the current that's going through the 6 kilo ohm resistor. It's going to be 6 milliamps times 0.66667, or 2/3, which is what that ratio is. And that gives me 4 milliamps, right? So 4 milliamps going through the 6K, and I'm going to put a prime on that. Why am I doing that? Because we're doing this, we're finding this out with just the current source in, but with the 9-volt voltage source not in there. So let's call that prime. We're going to have to add those up later. So I of the 6K is going to be 4 milliamps. I think everybody can see that I of the 12K then, just by parallelism, is going to be 2 milliamps. Or we could just say 6 milliamps minus 4 milliamps. Current's not being made anywhere in there. So obviously I've got 4 milliamps going through here, 2 milliamps going through here. That equals 6 milliamps. That's what we've got. So I'm going to put a prime on that too, because really this is just due to the current source. We don't have the voltage source in there anymore, do we? We replaced that with a short circuit. I could also find out, since I know it's 6 milliamps, I can find out the amount of current that's going through the 14K and the 35K too. So just doing that exactly the same, I'm going to say I prime of the 14 kilo ohm resistor is 6 milliamps. I like to write this out so that you can see, you know, really what I'm doing down here. I'm not hiding anything. So the 35 is going to stop current. This is going to allow current. We use the inverse lever rule. If we want to find out what's going on in the 14, the current through the 14, it's going to be the total current. But now it's going to be 35 kilo ohms divided by the total. 35 and 14 is 49 kilo ohms, right? So when we do that, we get the 6 milliamps times 35 divided by 49. And that gives me 4.286. 4.286 milliamps. And that means that I prime for the 35 kilo ohm resistor is going to be 6 minus that, which gives me 1.714, 1.714 milliamps, right? And so this is all happening again. I just want to point this out. In us having replaced that, having replaced, I'm going to divide this out too, because we've now done it this way, right? Replacing this, but don't we have to replace this one too so that we can compare, we can find out what those are as well? You know, if I take this out of here, that's just going to make this be a huge open circuit over here, isn't it? Any current going to flow out of here if I've got a big hole in my circuit right here? Big hole. Right? What if I put a big hole there? Well, nothing's going to flow out here, is it? Not at all. So let's put this back, but let's realize now that if I was to put an open circuit here, there would be no current that flows at all outside of that. So really what I have to analyze now is this. Right? This is my 9-volt supply right there. And what I want to do now is I want to find out what the currents are in that. I think everybody can sort of see what we've got here. I've got 9 volts here, and so I've got 9 volts here, and I have 0 volts here, right? 9 volts there and 0 volts here. So I can pretty much figure out what the current is that's going to be flowing through. Because if I wanted to find out, let me just get my red pen for a second. If I wanted to find out the current that's flowing through here, isn't this just 9 volts? Isn't that the voltage drop across there, 9 volts? And then I have 6 kilo ohms and 12 kilo ohms, which gives me 18 kilo ohms. So the current, I'm going to put 2 primes here. The current flowing through the 6 kilo ohm equals the current that's flowing through the 12 kilo ohm equals whatever 9 volts divided by that total resistance is, right? So 9 volts divided by 6 plus 12 kilo ohms is 18 kilo ohms, right? 9 volts divided by 18 kilo ohms. I'm going to do this, but I already know 9 divided by 18 kilo ohms gives me 500, well, 0.5, I want to work in milliamps, so I'm going to say it's 0.5 milliamps. All right, 0.5 milliamps. It's really 500 microamps, but 0.5 milliamps is just as good. Now, we also know that there's 9 volts right here, right? So we know that there's current flowing around this way, right? To go to 0, 9 volts going through the 14 kilo ohm plus the 35 kilo ohm. So I know, I'm just going to put a line here, I know that the current, due to us situating it, getting rid of the current source and replacing the voltage source, I know that the current through the 14 kilo ohm and the 35 kilo ohm, right, are going to be going in this direction. And we have to figure out the direction, of course, up here, which way those were going. And I'll draw them over here in just a second. But that's just going to be the 9 volts. And again, divided by the total current in that circuit. So 14 plus 35 is 49 kilo ohms. Okay? So 9 volts divided by 49 kilo ohms gives me 0.1837. 0.1837 milliamps. And we can see which direction they're flowing in. All right, now let's take each of these. Let's look at the direction that these are flowing in as well. We've got the current source now. We got rid of this. So we know that all of the currents that we're talking about are flowing right in this direction through all those individual resistors. Right now, what I want to do with the green pen, that's for this. What I want to do for the green with the green pen is I probably should have drawn those in green. Right, that might help. What I want to do with the green pen is I want to now draw these. Now this is still going in that direction, isn't it? But over here, it's working opposite to that direction. This is going in this opposite to this direction, but over here, it's going with that direction, isn't it? So let's figure out what the totals are. So when I look at the current that's flowing through the 6 kilo ohm resistor, it's going to be I prime 6 kilo ohms plus I double prime 6 kilo ohms, right? Wait, 6 kilo, oh, I'm sorry, that's supposed to be a minus. I will actually use, yeah, there we go, because I can always put a minus in there. So that would be minus that, because in the 6 kilo ohms, we got this one going down that way, and we've got this one coming up this way, right? So we look at the 4 milliamps minus the 0.5 milliamps, right? So that equals 3.5 milliamps. All right, let's do the 12K. So I of the 12K is just going to be, when we look over at the 12K, they're both going in the same direction. So it's going to be 0.5 milliamps plus, then we look up here for the 12K, I've got 2 milliamps. So that gives me 2.5 milliamps. Let's go down to the bottom now. We're looking at the current through the 14 kilo ohm resistor. And we see that the 14 kilo ohm resistor has, they're both going the same way, so it's 0.1837 milliamps plus, let's see, 4.286 milliamps. Did I get that right? 14? Yeah. Okay. So that ends up giving us, just a second, this is 4.286 plus 0.1837 gives us 4.47 milliamps, right? And we'll do the last one. So I of the 35 kilo ohm resistor, if we come up here, we see that's 1.714 milliamps from the current source analysis. And then from the other, I get plus 0.1837 milliamps. 0.1837 plus 1. Oops, wait a second. What, 35? Oh yeah. So we want the 1.714, but then we want this to be a minus. Thanks for catching me there. Actually, I can't hear you if you're yelling at me. And of course, you haven't even seen these for another couple of weeks anyway. So this is a minus. So, excuse me. We've added those together. Those were added together. Those were subtracted from one another. And of course, this one too is going to be subtracted. So I've got 1.714 milliamps minus 0.1837. And that's 1.53. 1.53 milliamps. And let's draw the directions of all of these. That would be down. For 12, that would be down. For the 4.47 in the 14, that would be going in that direction too. And the 3.5 in the 6 is, that's the 4, and that's, yep, so that would be going down in that direction as well. All right, so that's how we use superposition to, oh wait, you know, I'm trying to, 1, 2, yeah, how we use superposition to take out the current source, do it with the voltage, take out the voltage source, do it all with current, and figure it out. Now, what if those were two voltage sources? Could I take one out and leave the other one in and do that and then switch? Yes, absolutely. It doesn't matter if they're current sources or voltage sources. You take one out, you solve the problem without it there. If it's a voltage source, you replace it with a short circuit. If it's a current source, you replace it with an open circuit, right? And then do the analysis and then add the two together down here and it'll all work out fine. I just want to check, did I even turn that back on? I did. Boy, that's good. I just want to check something. I'll be right back.